Welcome back to After Hours Engineering. This is the second part in a two-part episode, Synthesis. In this episode, we finish up the memory component of our processor and synthesize our design into the FPGA. Along the way, we'll touch on these topics. There are at least three types of memory that we'll look at. Flip-flops, which is not listed here, registers, which are typically collections of flip-flops of the D-type variety, and we'll look at BRAM, which is what we are interested in with our memory synthesis. We'll also touch on inference versus handcrafted, and by that we'll look at the usage guide for the ICE40 and the ICE40 datasheet specific to the LP and HX family, which is on our device. We will also finally look at how we know we've activated the BRAM sections. We'll take a look at Yosys's output logs, NextPNR's output, and we might use the Icebox stat tool to look at what was generated. And most importantly, we'll look at the write Verilog command that we'll send to Yosys. Before we dive into the greater details, let's approach synthesis as we've done in the past. We won't concern ourselves with any resource requirements. As before, we'll start off by looking at our synthesis files. We only have three: the top, the make file, and the memory module itself. So we'll take a look at the make file first. We have our usual suspects. We have the top module, the memory module, our main module that we'll be synthesizing. All of our usual variables. We have one new variable here that also showed up in synthesis, and that is the IceStorm toolchain, and that includes the compiled version of Nexus and Yosys. We still have our Yosys command, our targets, our pin constraint file, and here is where we now use that toolchain right down here. That's pretty much it for the make file. It's kind of unchanged. We have our usual pin constraint, which we're using them all, and we have our top module. We also have our top module, and up above we have the usual defines for the net types, some undefinitions to turn off simulation. We're using pretty much all the output pins and input pins. Our usual definitions for memory, frequency, and what we're going to write to memory, some aliases, and our clock that we'll synchronize on. And then we have our first initial begin. Now again, this isn't really going to be honored here inside the top memory file. It's going to be inside of the memory module itself, which is where the initialize statement needs to be present. We'll get to that later. Here is the device under test, or in this case the device being synthesized, the actual memory module itself, which I'm calling ROM here. It's actually RAM. And then we assign all of our outputs. So this top file is fairly similar to all the other synthesis modules that we've done. And finally we have our most important module, the memory module itself. It is literally the module we use to simulate. Nothing is really different about it. We still have our memory. We have dumping of outputs which won't occur during synthesis. And we have the same synthesis block for single port RAM, and that's it. We also have our microcontroller program shown here. This is used to send signals to our FPGA to control the hardware. As usual, we have a few keys to find for sending and setting signals, the usual clock and toggle reset. We can also set our address that we're going to send to it. We'll cover that in a minute. And finally, we have the case statements that do the actual work themselves. There's really nothing special about this module. You can use anything you want as usual, but this is what I'm using with and I'm familiar with. We also have our LED outputs that we have connected to our FPGA here. We have the lower 8 bits of the data right here. We have the two address selector bits right here, and then the write enable bit here. Next is building, routing, and uploading our design onto the FPGA. So we come over to the terminal and we're going to run the build first, and there it goes, it just ran. Now we're going to run the route command and let it go. Now it has been run and built. So I come over here to the FPGA and I'm going to do a make upload here and hit the button and hit upload. Now it's erasing and writing to the bit stream. Watch the lights below. They'll blink a little bit, and there you go. It's been uploaded to the controller. Let's verify the upload by checking the memory locations. We know if we go to our memory module, we set up 4 memory locations with 4 values. Let's check those out. So we come over to the terminal here, and I'll hit the letter A, and that sets our address indicator to this address, or 00. And I hit the X key, and all the lights go on. That's because at memory 0, we have 2 FFs right here. So let's check the next one. We should see the upper 4 bits and the lower 4 bits opposite of each other. So I'll switch the addresses to 01. So I'll hit the letter B and then clock it with the letter X. And there you go. We have FF or F0. And we can check that for the next address, which we happen to know is 0F. So let's do that. We'll hit the letter C for the third address, hit X, and sure enough, the lower 4 bits are high. And of course the last address, which is FF, we'll do that one. That's the letter D on the microcontroller. So I hit D and I hit X, and there it is. That's the bottom of memory, which has 01 in it. So we verified that the read of memory is working. Let's check to see if the write works. We'll set our address back to 00. So we'll come back over here and we'll hit the A key and hit X, and they all went high. But now I'm going to hit my W key, and that's going to set the write enable low. So I set that low, I hit the X key again, and guess what? We just wrote a 5.5 to that memory location. Now I'm going to turn the write enable off, which highlights the LED again, and clock it, and nothing will happen. Why did it write 5.5 to there? So if we scroll up to the top, this is our write data, and 5.5 is the same thing as alternating each bit on and off. And if I come down here to write data, you can see that the data in is set to write data. So yay, it's both reading and writing to memory. We successfully synthesized memory onto our FPGA, and even the initialize block was honored. The question is just what kind of memory was synthesized? Did we actually get single port RAM or something else? Perhaps we just consumed a boatload of registers, or maybe we utilized something more efficient like RAM. We should investigate what just transpired. So even though our Verilog code looks much like a bank of registers, the toolchain may infer it as something else entirely. We need to satisfy the pattern the toolchain is looking for. Let's return back to our memory module, which we have right here, and take a look at different styles of memory allocation. At the start, we have a register, a plain old 1-bit register. That's memory, and most likely it will be synthesized as a D-type flip-flop. We also have a register, which is really nothing more than a bank of registers, and it may be synthesized as a group of D flip-flops, but it could also be synthesized as something special within the target hardware itself. And then finally we have the actual memory, which you've seen up to this point, and it looks just like another bank of registers. And it will be when we specifically avoid the patterns. But first we're going to try to look at what we can do with inferring patterns, because we're concerned with just memory and how the toolchain infers its way to synthesis. So we'll go ahead and remove these and set up for what we need. So how does the toolchain determine what to synthesize? Well, it's a process called inference, and it works by parsing your Verilog code for patterns. We can learn how to code for these patterns by looking at Appendix A of the ICE40 usage memory guide. If we look at our module and the style guide, which I'll bring up right here, you'll see that our Verilog code follows the single port RAM structure, albeit using a little bit of a different style guide. Scrolling farther down, we also have the dual port RAM configuration, and again our Verilog code follows the guide of the dual port. If we scroll down in our guide here, you'll see that we have the dual port RAM. But what happens when we don't follow the patterns? Well, let's find out by building our module, but this time we inspect the output that we have been conveniently ignoring up to this point. Let's change the code to use a continuous assignment. This will guarantee that we avoid any of the patterns that the inference engine is looking for. So we come over here to turn off our terminal and the output, we can see that we are back in our module. So the first thing I'm going to do is switch over our inputs to wires, and then I'm going to scroll down here to this, and I'm going to turn off the read portion of memory, and I'm going to come back up to here and switch on continuous assignment. This is something that you would probably do if you were just going about and creating a typical memory module. So we'll save that. Then I'll bring up the terminal here, and we'll run the tools again. Here we're running Verilog, and then I'll run the route tool. That's all we need to run. It's the first time we're going to take a look at the output, and here we are. We have 3 tabs. We have the Yosys output, we have the Verilog's write command output, and we have the next PNR output. So let's go ahead and reload these because they've already been loaded. And then for Yosys, we're going to scroll down to section 324 right here. And that's the memory pass section where it's going to try to make some inference. And you can see that it's detected our device it's a dual port memory device. And here it is beginning to go through all of the rule checks. It's attempting to infer some sort of memory that's specific to the device. And if we scroll down here, we'll see on the last line that it was unable to find any kind of BRAM type of resource that matches our Verilog code. And so this is telling us directly right here in the Yosys output that it's almost certainly is not going to use any hardware resources. So let's look at the write Verilog. So if we scroll down here to the bottom and we look for the SBRAM, we'll find nothing in there. But what we will find all over the place is a lot of ROM.memory things. And this is part of our Verilog code. This is our module, and this is the memory element inside of it. And you can see that there are a lot of assignments going on here, as well as right here. What Yosys has done has fallen back to basically allocating all of our memory as one giant chunk of actual registers, D flip-flop registers. So it isn't using any of the hardware. We can also check this by looking at the next PNR, and if I reload this and then go down to device utilization, we can see that the Ice Storm RAM, we have a 0 here. That's telling us that it definitely did not find or utilize any of the internal block RAM on the device. So we have effectively thwarted the inference engine to the point where it couldn't help us find BRAM on the device. Now let's switch our memory module over to using single port RAM. So we'll go ahead and switch the code back to a registry output. We'll scroll down here and turn off our assignment statement, and we will place the read back in the same behavioral block. This is single port RAM as we saw in the ICE40 spec sheet. So let's go ahead, bring up the terminal, and rerun the build tool and rerun the route tool. And again, we'll go back over to the log output and take a look to see what happened. So we'll reload that. We'll scroll down to 324. And again, our device is actually a dual port BRAM with 4K in each block. And we're again using the same address and data bit combinations. And here it is. It's going ahead and running a set of rules to find out what works. You can see that it's checking out the different styles. And each one of these ICE40 RAM here are defined in the spec sheet in a slightly different way, but they are defined in there. And I keep scrolling down, but this time you'll notice that it did successfully find a rule with an efficiency of 100%, and it chose that one. It's the highest efficiency. Now let's take a look at the Verilog code, and this time we'll again look for SBRAM, and sure enough, it has actually synthesized a BRAM, a block RAM, that's actually on the device. And here is our data that we put inside of our memory initialization block in our module. So far things look good. Let's take a look at the next log and reload that, and then look for device initialization. And sure enough, the ice storm RAM has been used. So yay, it looks like everything is good. However, it isn't. It is actually unable to infer single port RAM, and the reason is that my FPGA, the one we've been using up to this point, is an LP or an HX type of device, and it doesn't have single port RAM in it. It only has dual port RAM. So when we came and looked at this right here, you'll notice that this is actually mode 0, which is both of these modes are at mode 0. And if we go back to the spec sheet, it'll tell us that that is a dual port memory. So in this case, the toolchain fell back to trying to use the best thing that the device had, which in this case is dual port memory. And that's what it's telling us. So if we scroll back up to the top, you can see that it only sees the 2 dual ports. So in this case, we didn't get what we were expecting. Now hopefully, as an engineer and a design, you're using your target device, you will have probably perused through the tech sheet and you'll know what your device is actually capable of. We turn our spec sheet back on. I will scroll over to the spec sheet, and if we scroll up to the embedded section, we can see in the guide that there are a bunch of block RAM definitions, but all of them on our device are dual port memory. There are no single port memory. There you go. We now have suddenly discovered that the Inference tool fell back on us. Let's do dual port memory next. So we'll come back over here, turn off the tech spec, come over to our module, back over to our module here, and this time we're going to enable the dual port RAM. And I'll disable this, enable the dual port RAM here, save it, and then come back over and bring up our terminal, run our build command, and then run our route command. Now we'll take a look at the output of all of this, turn the terminal back off, and look at it. We'll reload the Yosys output and see what it did. So if we scroll down, you can see again that it has found 2 ports and the same set of properties for it. It goes through the same set of rules, and lo and behold, it has identified the exact same mapping that it wants to do. So nothing is technically changed. However, it is actually meeting our expectations. We wanted dual port RAM and we got dual port RAM. And it's also the same here. If I was to reload this and scroll down to the bottom for the SB RAM, we get the same thing. Now I'll note one thing here. If we go and look at this thing, it looks kind of weird. But if we look at the tech specs, it'll tell us that N and an R means negative edge read, and a N and a W means negative edge write. So if we go back to our Verilog code, so we'll hide that, and sure enough, we have a negative edge clock with a negative edge write. We also have a negative edge clock for reading as well. So things are actually lining up. I could change this to the positive edge and change this one to positive edge, and then this block RAM definition changes. But we'll leave it for negative right now. I just wanted to point that out. And again, if we look at next PNR, it should show us the same utilization as before. So if we search for device, you can see that it's identified one usage of the iStorm RAM. We just learned how to check the results of the inference, but can we specify exactly what we want and skip the inference? Yes, but I wouldn't recommend it. However, you can find out how to handcraft your memory by checking the spec sheets of the system section. Let's take a look. As an example, here's an instantiation version of our 256 by 16 memory BRAM block. You can see up here, just as a quick reminder, that the NR and the NW that we saw in our Verilog output means negative edge clock read and a negative edge clock write. And that's exactly what our Verilog code was doing here, negative edge and a negative edge. But down here we can see in the spec sheets a way to do it by hand. The toolchain is going to actually infer this for us. So if we scroll down here, I cut and pasted it a version of a hand-coded version. Again, I wouldn't recommend doing this. The best scenario is to have your toolchain infer for you. It gives you the best ability to move between different targets, because if you move to a different physical hardware target, you're going to have to change your code, versus the toolchain inferring the new code for you. So I highly recommend that you use the inference mode more often than not. And again, if we scroll down, you can see the different types of instantiation. And all I have to do in our Verilog code is change my address and data width, and the toolchain will infer each different mode for us. Now we know how to synthesize memory and know what we expected. We now have functional memory that we can integrate into our processor. And this gives us the third major component alongside our register and our ALU. In the next episode, we're going to tackle the next component, the register file, where all intermediate results are stored. Until next time.